Hi, welcome to Electrochemistry. This is our first part of this chapter. Today we're going to look at redox reactions. So you may have remembered redox reactions from Gen Chem 1. We kind of brush over them a little bit, but redox reactions actually touch our everyday lives. Anyone have a Galaxy phone? This would be an example of redox meets thermochemistry. See, Samsung Galaxy phones had some big issues a couple of years ago catching on fire, and that had to do with the energy that the reaction that was in the battery that was driving the electronics of the phone was a very exothermic reaction, and there was no ability for that heat that was being generated, the enthalpy that was coming from that spontaneous chemical reaction, to be dissipated. And so we saw a lot of these incidences where the Galaxy phones in particular are having a big issue with catching on fire. So today we're going to back up a little bit. We're going to talk about a redox reaction. So I'm just going to refresh your memory. How you know you have a redox reaction, you're going to assign oxidation numbers. I remember that fun stuff. We're going to learn to balance redox reactions. Before, in Gen Chem 1, you never had to balance redox reactions, and they can be quite challenging. So we're going to look at balancing redox reactions both in an acidic and in a basic environment. And then we're going to start talking about batteries and the different types of chemical reactions that are happening. So we have voltaic or galvanic cells, which are spontaneous reactions, and we have electrolytic cells, which are non-spontaneous reactions. One generates an electrical current, the other one runs off an electrical current. And then we're going to learn about potential differences and the units of cell potential. So that is our lineup for today. So first off, electrochemistry is driven by redox reactions. And a redox reaction, remember, is an exchange of electrons. In this chapter, we're going to use redox reactions to either generate an electrical current in a voltaic cell, or we're going to use an electrical current to drive a non-spontaneous reaction in an electrolytic cell. The first part of this, we're going to talk about voltaic cells. And so these are just some examples of some redox reactions that you may have come across. So down here is our classic rusting of irons. This is corrosion. And so that's a spontaneous process that happens without any intervention from us. This would be evidence of a chemical reaction. Here I have a metal that's dissolving. This looks like a magnesium ribbon, maybe in hydrochloric acid, and so it's generating hydrogen gas. Those bubbles that you see, that's a spontaneous reaction. It's also a redox reaction. Our hybrid and full electric cars are utilizing redox reactions. And then also, any kind of fuel cell that you might have, that's a redox reaction. So these are an important classification of reactions that we kind of brush over in Gen Chem, but we're going to come back and really focus on them in this chapter. All right, so you might remember oil rig is going to allow you to keep track of what is the oxidation, what's happening at the oxidation half, and what's happening at the reduction half. And remember, these are redox reactions. They deal with a transfer of electrons between your reactants and your products. And so something is going to lose an electron, something is going to gain an electron. Sometimes it's easy to see that you have a redox reaction. If I take sodium metal, for instance, and I react that with chlorine gas, and I form sodium chloride solid, this is a classic redox reaction because sodium has lost an electron, chlorine has picked up an electron and formed this ionic solid, which is really sodium ions and chlorine ions. And that's easy to recognize as a redox reaction, but not all redox reactions are easy to recognize. For instance, the combustion of methane is also a redox reaction. Even though I'm not forming an ionic compound, I'm transferring electrons in this. Oxygen, in this case, is being reduced, and carbon is being oxidized. And so it's really hard to tell. So we're going to look at assigning oxidation numbers, and that's going to help us tell whether we have a redox reaction or not. So an oil rig is oxidation, that's one half, is the loss of electrons. So if I'm losing electrons and being oxidized, so sodium in this case goes from sodium with the zero charge to sodium plus one, it's lost an electron, so sodium has been oxidized. Reduction is the gain of electrons. So in the formation of sodium chloride salt, chlorine is being reduced because it's picking up an electron to form a negative charge. So I can have the formation of ions, and that's easy to track my electrons, but I can also have covalent molecules where electron density is being shifted within that reaction, and it's a little bit harder to keep track of what's going on. So I'm going to assign oxidation numbers. And assigning oxidation numbers is going to allow you to track where your electron shift is happening, and it'll also allow you to determine if you have a redox reaction or not. So in Gen Chem 1, what you should have done is done just some basic redox reactions where you assigned oxidation numbers, and then you saw what was oxidized and you saw what was reduced, and you didn't have to worry about balancing or anything else. And so we're going to build on that. So before we do that, let's just review the rules for assigning oxidation numbers. So my first rule is if I have a single element, and I'm talking about an element that is not in a compound, or I have a diatomic molecule, my oxidation number is going to be 0. And some examples of this might be sodium solid, right? That's just a single, or chlorine gas, my diatomic. Both of these are going to have an oxidation number of 0. Things that are just a single element or diatomic, then where they're occurring in their natural state, those are going to have an oxidation number of 0. And my oxidation numbers, it's a way to sort of track electron density change. So it's kind of a bookkeeping method. So my second rule is if I have a monatomic, mono meaning one, a monatomic ion, my oxidation number is going to equal the charge of the ion. So when I form sodium plus 1, my oxidation number for that is +1. When I form chlorine -1, my oxidation number is -1. Oxygen -2, it's -2. So a monatomic means one atom. If I have a one atom ion, my oxidation number is going to equal the charge of that ion. My third one is oxygen is going to have an oxidation number of -2 if it's in a compound. And that would be something if I had magnesium oxide, for instance. My oxidation number in this for magnesium is going to be +2. My oxidation number for oxygen is going to be -2. That's easy to see in an ionic compound because that's also the charge. But what if I have carbon dioxide, for instance? Now my oxidation number for each of these oxygens is going to be -2. So I have 2 oxygens in there. Each of them is going to have an oxidation number of -2. If I have carbon monoxide gas, that oxygen is going to have an oxidation number of -2. There are some exceptions here. If oxygen is in a peroxide, so peroxide, remember, is a polyatomic ion where I have 2 oxygen atoms and it has a -2 charge, then the oxidation number for oxygen is -1. Or if it's in a compound with fluorine, because fluorine is more electronegative, oxygen is going to have a +2. So hydrogen has an oxidation number of +1 in a compound. So for instance, water, oxygen is going to have an oxidation number of -2. Hydrogen is going to have an oxidation number of +1. And there happens to be 2 hydrogens, so when I look at each one of these oxidation numbers, it's going to balance, they're going to balance out. If hydrogen is in a metal hydride, say NaH for instance, this is a metal hydride. In this instance, my oxidation number is going to be equal to -1 in a metal hydride. So I could have sodium hydride, I could have magnesium hydride. My oxidation number for each of these hydrogens is going to be -1. So that's also another exception that we're not going to run into very much. My fifth rule is if I have a binary compound, binary meaning 2. If I have a compound that's made up of 2 elements, the element with the greater electronegativity has the negative oxidation number. So you may have noticed by now that we're assigning either negative or positive oxidation numbers. And so if I have a binary compound, fluorine is going to be much more electronegative than sulfur. Sulfur has an electronegativity of 2.5. Fluorine has an electronegativity value 4.0. So it's far more electronegative. So this is going to have my negative oxidation number. That's going to mean sulfur is going to have my positive oxidation number, and this is going to be a -1 for fluorine. And then sulfur, in this case, is going to be a +6, and we'll talk about why that is. So number 6 addresses that. In a neutral compound, the sum of the oxidation numbers equals 0. So in this case, I have 6 fluorines. Each of those fluorines is going to have a -1 oxidation number. So the sum here coming from fluorine is -6. So this is a neutral species. So to balance that out, sulfur is going to have a +6. If we go go back to carbon dioxide, for instance. We said that each one of these oxygens is going to have an oxidation number of -2. There's 2 oxygens. So that means total, I'm going to have a -4 coming from the oxygen. That means my oxidation number for carbon has to be a +4 to balance that out. If I look at carbon monoxide, now carbon monoxide, this oxygen here has a -2. Now my carbon must have a +2 to balance that out. So the sum of a neutral species is going to be 0. So if I have something where I don't have a specific rule, I don't know specifically anything about carbon, I'm going to look at what carbon is with to assign that oxidation number. So the sum of the oxidation number is going to equal the charge of the ions. And this is going to come into play with those polyatomic ions. So if I have something like SO4 2-, the sulfate polyatomic ion, each one of these oxygens is going to have a -2 oxidation number. There are 4 of them, so total coming from my oxygen here is going to be a -8. Because I have 4 of these, each one of these oxygens has an oxidation number of -2. If I sum up my oxidation numbers coming from oxygen, it's going to be -8. I have a charge of -2, so that means that sulfur is going to have a positive charge, but it's going to be a positive charge that balances this but leaves a -2 left over. So in this case, sulfur is going to be a +6. If I look at SO3, the sulfite polyatomic ion has the same charge, but now I only have 3 oxygens. Each one of these oxygens is going to have a -2. That's going to give me a -6. So sulfur in this case is going to have a +4. So those are our rules for assigning oxidation numbers. Probably going to help you a lot to sort of keep those in mind as we go through these reactions, these redox reactions. So the first step is realizing that you have a redox reaction. If I look at just calcium and I drop that in water, I'm going to see bubbling. That calcium metal is going to start to bubble. If I were to take the pH of that water, it would be basic, because I'm forming calcium hydroxide, and that's aqueous in solution. So I'm releasing hydroxide ions, and that bubbling that you're going to see is hydrogen gas. This is also a redox reaction. And let's assign oxidation numbers, and that's going to help me determine if this is a redox reaction. And I also want to know what's being reduced and what's being oxidized. So calcium is going to have an oxidation number of 0. Oxygen in a compound, we said, is going to have an oxidation number of -2. Hydrogen is going to be +1. You'll notice that I'm not putting a 2 here because I'm looking at these individually as an individual atom. So I don't really care about the sum that's happening here. I just want to keep track of each one of these hydrogens has a +1 oxidation number. If I come over, this calcium has a +2. Then I look at this hydroxide. And remember, hydroxide has a -1 charge. So when I add up the sum of my oxidation numbers for hydroxide, I want to have a -1 left over. Oxygen is going to be a -2, and hydrogen is going to be a +1 in here. And when I add those up, because it's a 1-to-1, I'm going to get a -1 charge left over. I don't care that there's 2 of them. That balances my ionic compound, but I'm really looking at each one of these individually when I'm signing oxidation numbers. I'll come back to this too in a bit. And that's a 0 because it's a diatomic. And so now I'm going to look and see what was reduced. Your oxidation number is going to reduce. In oxidation, your oxidation number is going to go up, increase. So I just think reduce, reduction for your oxidation number. So I have calcium goes from 0 to +2. That is 1/2 of my redox. And hydrogen goes from +1 to 0. So in this example, this is being reduced, my oxidation number here. This is my reduction half. And calcium is increasing because it's going from 0 to +2. It's my oxidation half. So I can break this out into half reactions. First, I'm going to identify what was oxidized and what was reduced. And then remember, we had these things called the reducing agent and the oxidizing agent. A reducing agent is whatever is reducing the other thing. So if I'm a reducing agent, then I'm undergoing oxidation. And so my reducing agent would be calcium, solid calcium, because it's undergoing oxidation. My oxidizing agent, I could say hydrogen, or if I wanted to, I could say H2O, but really my reducing agent is the hydrogen. The oxygen isn't really having a change in oxidation numbers. All right, so we want to balance redox reaction. So this one, if I balance this one, this would be really easy, right? I could just put a 2 here, and then I balance my hydrogens, I balance my oxygens, my calcium's balanced. And this is a very simple redox reaction where I can just look at it and balance it, but that is not going to be the case because a lot of these reactions are very complicated. And complicated in the number of electrons that are being transferred, complicated because you could have water as a product or a reactant. These are usually happening in an aqueous solution. And so we're going to piece these out. We're going to separate them into the half reactions, the reduction half reaction, the oxidation half reaction, and then we're going to balance those into, well, the first thing I'm going to do is I'm always going to I'm going to assign oxidation numbers. Then I'm going to identify what my oxidation half and what my reduction half is. Then I'm going to pull those apart and write them as half reactions. And in this chapter, a lot of what you're going to see is spectator ions are probably going to be removed from the reaction. So you might see everything be neutral here, or you might see a reaction copper ion in solution, and I have solid aluminum metal that I drop into that solution, a transfer of electrons where I form aluminum ion and solid copper. And so what I've done here is maybe this was copper nitrate. I've just removed the nitrate because it's a spectator ion. It's not going to be really involved in that redox. And so you'll see a lot of these reactions that look incomplete because you're dealing with ions and you're forming ions, and the spectator ions have just kind of been removed because they're a lot of just noise. So in this one, let's assign oxidation numbers. So this is a monatomic ion. So my oxidation number is going to be equal to the charge. This is an element in its standard state, so that's a 0. Now this has gone to an ion, and this has gone to solid. And so let's look at what was reduced. So copper went from +2 to 0. So it had a reduction in its oxidation number. That was my reduction half. Aluminum went from 0 to +3. This was oxidized. So this is my oxidation half. I'm just going to pull these out and I'm going to write them as their half reaction. So my oxidation half reaction and my reduction half reaction. So I'm going to separate them into half reactions, and I'm going to balance my mass. So I have one of these to one of these, one of these to one of these. My mass is balanced. I'm going to also write in the electrons. Aluminum to go from 0 to +3, it had to have lost 3 electrons. For copper to go from 2+ to 0, it would have had to gain 2 electrons. And so even though my masses are balanced, and I look at this reaction and I think, oh, this is balanced, my electron transfer isn't. The oxidation half is releasing 3 electrons. My reduction half is gaining 2 electrons. So I need to balance my electrons, my charge as well. So in order to do that is I'm going to multiply this whole thing by 2 and this whole thing by 3. And that's going to allow me to balance my electron transfer. I just found the least common denominator of 6. And now my half reactions look like this. And once I've balanced my masses, I've balanced my charge, then I can add these back together to get my overall reaction. And this is my balanced redox reaction. If I had just looked up here, I would have thought that this is balanced because we're used to just looking at the mass, but I also have to balance in a redox. I have to balance the electrons that are being transferred. The electrons that are lost in the oxidation have to equal the electrons that are gained in the reduction. And so balancing these in half reactions allows me to do that. Then my last step, I'm going to combine them together. So I'm going to do one that's a little bit harder, and then we're going to talk about the solutions that these are in. I want to balance this in terms of redox. What I'll notice right away is that I have a transfer of electrons that's happening between my ions. I'm going from iron 2+ to iron 3+, and I also have the permanganate polyatomic ion here, but I just have manganese ion here. So I've lost an oxygen. I'm going to walk you through the steps to balance this redox reaction. And these are the steps that you should go through when you're working through the problems. So the first step is I'm going to assign oxidation numbers. So I'm going to assign oxidation numbers to all atoms. So this is an ion. So my oxidation number is going to be equal to the charge. This is oxygen in a compound. So it's going to have an oxidation number -2. Manganese, I'm going to look. So this is an ion. So the sum of my oxidation numbers has to equal the charge of the ion. So that's a -1. So this, since I have 4 oxygens, that would be total -8. that means manganese is going to have to be a +7, so its oxidation number is a +7. Manganese over here now is just an ion, and its oxidation number is +2. So I've assigned all my oxidation numbers. I'm going to identify my redox half reactions. So I'm going to track what was oxidized and what was reduced. So iron goes from 2+ to 3+, so its oxidation number increased. So this is my oxidation half. Manganese went from +7 to +2, so its oxidation number went down. This was reduced. Pull these out of here and write them as my half reactions. So my oxidation half is, and my reduction half. Now I'm going to balance my mass. I'm going to look at my main elements here. So I have one of these and one of these, so that's balanced. I have one of these and one of these, that's balanced. But I have oxygen on this side, so I need to balance the mass of my oxygen. So to balance specifically for oxygen, I'm going to add waters to the other side. So I have 4 oxygens, which means I'm going to need to add 4 waters, because that's going to balance my oxygens here. Now I've introduced hydrogen. So to balance my hydrogen, I'm going to add hydrogen ion to the other side. So I added waters on this side that introduced hydrogen. Now I'm going to have to balance the mass of my hydrogen. I have 8 of them. I'm going to add 8 hydrogens onto this side. But I'm not just going to add hydrogen, I'm going to add hydrogen ion. So my assumption is that this is in an acidic environment. If it isn't, I'm going to take care of that later, but I'm going to worry about that at the very end. So I'm going to make things easy, and I'm just going to add hydrogen ion here. So the 4th step that I'm going to do here is I'm going to balance the charge, and that's at electrons that are being transferred. So in this case, to go from a +2 to a +3, I had to have lost 1 electron. To go from a +7 to a +5, I have to have gained 5 electrons. So I'm going to add 5 electrons onto my reactant side here. I didn't leave myself enough room. So now I need to balance these charges. I need to balance the electron transfer. So if I have 5 electrons that are being transferred in the reduction half, I have to have 5 electrons that are being donated. That means that this whole thing then is going to be multiplied by 5. Now once I balance my mass, I balance my charges, then I'm going to sum up half reactions. Draw a line here, and I'm going to write everything that's a reactant. So I have 5 iron 2+ plus MnO4- plus 8 hydrogen ions. And those are all my reactants. And then my products, I'm going to have 5 iron 3+ plus Mn2+ plus and 4 waters. And that would be in an acidic environment. So unless you're told otherwise for these balancing chemical reactions, these redox reactions, you can assume that you have an acidic environment unless you're told basic. So if I'm in a basic environment, this will be the last thing that I do, is if basic, I'm going to neutralize my hydrogen ion with hydroxide, but I need to add to both sides. So I can't just add hydronium ion to one side, I have to add it to both. So if this is in a basic solution, what I'm going to do is I'm going to neutralize these by adding 8 hydroxides to my reactant, but I also need to add 8 hydroxides to my product side. So I can't just add them to one side. So that makes this is then going to form 8 waters. And since I have 4 waters here, 4 of those waters are going to cancel out. This whole thing is going to go away, and I'll have 4 waters. And this would be my balanced redox reaction in a basic environment. So we're going to do some of these in our Zoom meeting. It might be helpful just to verify that I've done this right. So to verify, maybe that'll be our 7th step, is to verify. I'm just going to count mass and also count charge. Reactants versus my products, I'm going to look at all of my species that I have. So I have iron, manganese, oxygen, and hydrogen. I have 5 irons here, I have 1 here, I have 4 plus 4, I have 8 oxygens and 8 hydrogens. And then on my product side, I have 5, 1, 8, and 8. So I'm balanced from a mass standpoint. Now I want to balance from a charge. So on my reactant side and my product side, so I'm just going to look at the charges here. I have 5 times 2, so I have a plus 10, minus 1, so I have plus 9. And then over here I have 15 plus 2, That's 17 minus 8, which is also going to give me 9. So my charges balance, that's my verification. All right, so balancing redox, and these can be terribly, terribly complicated. We'll do a couple of really interesting ones in our Zoom meetings together, and you probably have 1 or 2 interesting ones on your homework. So if you get stuck, go back to those steps and think about what's happening. What's your redox solution?